lecture is about classifying chemical reactions. And I am going to, at the end of this lecture, I'm going to play this video, but this is also in your notes. And it's a really good video to go over these reactions. So we're going to look at each one of these individually here in just a minute. But just so you kind of have an idea of what we're going to see, we're going to look at a combustion reaction, which is a carbon-containing compound added with oxygen to create CO2 and H2O and heat. Okay, think about something combusting. We think of heat being released. We go then to combination reaction. This is also called a synthesis reaction. And it's when two or more things are added together. So we have A plus B to get one compound, AB. We then have decomposition, which is the opposite. So I'm starting with a compound, and it's breaking down into what it's made of individually. Then we get down to, these are my favorites, single replacement and double replacement. I like to call these single date swap and the double date swap. So what happens here is I have a loner A on the left side, and we have a loner C on the right side. But how did this happen? Well, A came in and it kicked out C. So then my compound on the right-hand side is then, since A took C's spot, it's AB, and poor C is ditched. The double date swap, I have A, D, so this is a metal, right? And D is my non-metal. Well, they break up. Well, so does my metal and non-metal CB. They break up. Well, then they're going to rejoin. But two metals can't join together to make a compound, so A and C are not going to be partners. A is going to combine with the other non-metal. So then over here I have AB. And then it's not DC because we always have to start with my metal in a compound, right? Metal and then non-metal. So C is the metal since it's listed first here. So then it'd be CD. So two dates, they split up and then they rejoined with one another. So that's the 5. This is kind of like a sub-chemical reaction, neutralization. So it's when I have a acid, so it starts with H, which is my acid, and then added with a base, which notice that it ends in OH. So I have an acid, starts with H, a base, and OH. And then what happens is that H joins with the OH to make HOH, which is H2O. And then I have my metal joined with that non-metal. So it's also a double replacement reaction. It's just a specific double replacement reaction that ends up with water, and it's with an acid and a base. So let's get a little bit more into the nitty-gritty of a combustion reaction. It's a chemical change that consumes oxygen and produces heat as light or energy. We have a carbon-containing compound plus O2. And what's happening here is, this is my carbon-containing compound. I'm going to have CO2 and my organic compound, which is a hydrocarbon of some kind. In the video, it says one of the most popular or one of the most basic combustion reactions is with propane, which is C3H8. So we have a hydrocarbon here. So there's the carbon getting split over here and my hydrogens. Because remember, chemical reactions have to follow the laws of conservation of matter, where I can't create or destroy matter. Whatever is on the reactant side, I have to have on the product side. Here's another hydrocarbon. We can see CO2, H2O, and heat. And then here's another example. This is glucose, which is what's in our body, sugar in our body. And so we know that when combined with oxygen, it's also going to produce CO2, which we exhale, right? We breathe out carbon dioxide, water, and the heat or the energy that we produce, which is called ATP. Here's another, here's fuel, combustion. Here is our combination reaction, a reaction in which simpler substances are combined into a more complex compound. So we're going from simple, so individual. So here I've got A here plus B to give, so I've got my blue and my red, and it combines to form a compound with blue and red. I mean, it's pretty, here I've got magnesium plus oxygen. With some heat, it's going to create magnesium oxide. Now, there's a couple different ways that combination reactions can happen. We can have a metal with oxygen. So like that example, magnesium plus oxide gives me magnesium oxide. So metal with oxygen. We can have nonmetals with oxygen. So I can have sulfur plus oxygen to give me sulfur dioxide. So this would be a covalent compound. So we can have an ionic compound. We can have covalent compounds. So combination reactions are not limited to just one, kind of reaction. It can be ionic, it can be covalent. And here's an example with not including oxygen. We can just have a metal with a nonmetal. We can have lithium plus bromine to get lithium bromide. Since it involves a metal, this is also an ionic. But all examples of taking two individuals or two simple things and making them more complex. We can also form a hydrate. So if I said, go hydrate yourself, right? Or you are dehydrated. If you need to go hydrate, you need to drink water. If you are dehydrated, that means that you are without water. So forming a hydrate means forming a compound that has water in it. And notice that in this example, I'm taking barium chloride plus water. So I am taking two, not as simple as just barium plus chlorine to make barium chloride. No, it's a little bit more complex than that. But I still am taking 1 plus 2 individual things, or actually let's call it 1 individual thing plus 1 individual thing to create a larger substance. So let's say 1 plus 1 is equal to 2. So this is larger. This is barium chloride plus 2 waters to give me barium chloride, and then we would say this is called barium chloride dihydrate. That's how we would say that. So, and notice that little dot in between the two, that is a connecting. That connects that whole compound. So that's barium chloride dihydrate. Let's move on to decomposition reactions. And I kind of told you in the intro that this is pretty much the opposite. So decomposition is taking a complex compound, breaking it down into 2 or more simpler substances. Heat is often needed to do this. Going and looking at that example with our magnesium oxide, now imagine just doing this in reverse. Starting with our magnesium oxide, using heat and breaking it down into magnesium plus oxygen. So we're just taking the red, the blue, breaking it apart into red plus blue. Another example here is taking mercury oxide and breaking it down into mercury and oxygen. Notice, law of conservation of matter still exists, even though we're breaking it down. On the left, I have 2 HGOs, mercury oxide, mercury oxide. And on the right, I have, so this is 2 mercuries and 2 oxygens. On the right, I have 2 Hgs, so 2 mercuries, and an O2, which is 2 oxygen. 2 and 2 on the left, 2 and 2 on the right. Here's another example of taking calcium carbonate, CaCO3, and it's breaking down. So I'm starting with 1 reactant, and it's breaking down into calcium oxide and CO2. So it's not breaking it down into calcium and carbonate, it doesn't have to do that, but it is breaking calcium carbonate into calcium oxide and carbon dioxide gas. And we can see that on the left we have 1 calcium, on the right I have 1 calcium. On the left I have 1 carbon, on the right I have 1 carbon, and on the right I have 1 O plus 2 O's is 3 oxygens, and on the left there's 3 oxygens. So we're still following that law of conservation of matter. Then, opposite to forming a hydrate, we can break apart a hydrate. So now we're going to look at that barium chloride dihydrate, and we're going to break it into barium chloride and water. So we're just doing the reverse. We're breaking apart this one hydrate into what made it up. And then moving on, like I said, to my favorite 2, my single replacement reaction. So I've got, what happens here is I have a more active metal. It's going to kick out a less active metal. And I would give you a sheet that shows you which metals are more active. Which one would kick it out? So for example, if I said, I've got iron all by itself, and then I'm going to add it to this compound that's copper sulfate. Now, if that iron is more reactive than copper, so that iron is going to go, excuse me, I am going to take your spot. So copper sulfate now becomes iron sulfate. And then that poor copper, it was kicked out, so copper is by itself. We can then look at another example where I've got iron plus hydrogen chloride. So we would go, all right, Fe is going to kick out H. So it's going to be, instead of HCl, over here we're going to have the iron and chlorine together. So iron will come in, kick that out, and then poor H will be by itself. But remember, H can't be singly by itself because it's in Brinkelhoff. It's a diatomic when it's solo. So it'd be H2. And then we have to make sure to go back and balance the equation. Again, we haven't done anything with balancing. We will do balancing. This is just recognizing types of reactions. So I just wanted you to, be able to recognize that. Then let's look at double replacement reactions. What's happening here is we have 2 ionic compounds in aqueous solution. They switch anions. 2 people go to the prom and they swap the dates. Anyways, what happens is they produce an insoluble substance, which means it produces a solid precipitate. Here's a whole bunch of really cool solid precipitates, or precipitates, whatever, over here on the right from double replacement reactions, and they can be really pretty. So essentially, and you don't need to be confused, don't be confused about this. I've got barium chloride and potassium chromate. Essentially what's going to happen is you can either swap the chlorine and the chromate. So then I would have barium chromate instead of barium chloride. So over here. And then potassium would be with the chloride, potassium chloride. So notice we're just swapping, or if you wanted to swap the cations, so let's say, okay, barium and potassium are going to swap. So then K is going to come over here. So I would have K, potassium and chlorine, which is right there. And then Ba is going to come over here. So I'm going to have barium chromate right there. All right, another example, I have sodium carbonate, calcium bromide. So again, we just need to find either the cations or the anions and swap them. So instead of sodium carbonate, it's going to be calcium carbonate. And there's my calcium carbonate, my sodium bromide. Here's my sodium. It's not with carbonate anymore. Sodium is going to be with the other anion, sodium bromide. Neutralization. We said that this is also a double date swap. This is a double replacement reaction. a type of double replacement where the cation of one compound is H+, the anion of the other is OH-. What happens is I have an acid and a base. We know it's an acid because it starts with H. We know this is a base because it ends in OH. Therefore, when H ditches its anion and the OH ditches its cation, HOH makes H2O. So water is a product. And then this compound is a salt. So that's just a real specific type of double displacement reaction or double replacement reaction. Same thing. So again, here's just being able to pick it out. I would look at this, and at first I would go, oh, I've got H and SO4, K and OH. My first instinct is going, yeah, it's a double replacement. Okay, let's swap here, swap these. So I'm going to have H is not going to be with SO4, H is going to be with OH, and that's when I go, oh, okay, well, water. So yep, this is a neutralization reaction when water is produced. And then my other is a K with SO4, and that's my salt. So then again, I would look at this and go, I've got H and Cl, Ca and OH. So my OH is going to swap with the Cl. Do that. So OH is going to be with H to form H2O. And then calcium is then going to be with my chloride, calcium chloride. Hopefully, going through those chemical reactions made sense. Go back, look at them, be able to classify 6 different types of reactions. And next in this lecture, I'm going to play this video. Again, I recommend you watch it. It actually is really good.
Studying chemical reactions helps us understand and explain how the natural world works. Chemical reactions turn that slice of pizza you ate into fuel for your body, make dazzling firework displays on the 4th of July, or can even stop cancer cells from multiplying. In a synthesis reaction, or combination reaction, 2 or more substances combine to form a single product. You can use the generalized formula A plus B yields AB to predict the products of a synthesis reaction. Here, aluminum is mixed with iodine. Aluminum is covered with an oxide layer, which protects it from constantly reacting. However, a little water removes that protective layer and enables the reaction to take place. Initially, you see the purple iodine gas released, then aluminum sparks, and finally, a product, aluminum iodide. Photosynthesis is fundamental to life on Earth. Through this synthesis reaction, plants produce glucose, which they use for energy, and oxygen. Without this process, we wouldn't have food to eat or oxygen to breathe. A decomposition reaction is the opposite of synthesis. During decomposition, one substance breaks down into 2 or more separate substances. The generalized formula is AB yields A plus B. Here we have hydrogen peroxide with a catalyst added. If left alone, it would decompose over time, but adding a catalyst accelerates its decomposition into water and oxygen gas. During a car accident, airbags deploy in under 50 milliseconds using a decomposition reaction. Upon impact, the solid sodium azide decomposes and inflates the airbag. A combustion reaction occurs when a substance reacts with oxygen to produce energy in the form of heat or light. When combustion occurs with an organic compound, the products are almost always CO2 and H2O. Here we infused bubbles with methane gas. When heat is added, it triggers the combustion of methane. Our final products are carbon dioxide and water vapor. Without combustion, we wouldn't be able to enjoy summer barbecues. The combustion of propane is the most common reaction used to ignite your grills. The heat produced from the reaction allows us to cook up our hamburgers and hot dogs. A single replacement reaction, also called a single displacement reaction, occurs when one element replaces another element in a compound. The generalized formula is A plus BC yields AC plus B. Here we placed a copper wire in a silver nitrate solution. Copper is more reactive than silver, so it replaces the silver in the silver nitrate. Our products are copper 2 nitrate and silver crystals. You can see the silver crystals beginning to accumulate on the wire and the solution turn blue from the dissolved copper. Thermite reactions, a type of single replacement, are crucial for maintaining railway tracks. The intense energy generated during the reaction produces molten metal, which is then used to fill gaps between tracks. In a double replacement reaction, also called a double displacement reaction, the positive ion of one compound replaces the positive ion of the other to form two new compounds. One of those products is always a gas, water, or precipitate. The generalized formula is AB plus CD yields AD plus CB. When potassium iodide is added to lead 2 nitrate, the potassium and lead swap places. You can observe the yellow lead 2 iodide precipitating from the potassium nitrate. Eating a huge meal can put pressure on the ring of muscle that keeps stomach acids from moving in the wrong direction. So juices from your last meal may come back to haunt you in the form of heartburn. Luckily, antacids help soothe the burn. During this double replacement reaction, the calcium hydroxide from the antacid neutralizes stomach acid. Imagine a universe without chemical reactions. The ingredients in our pizza would stop growing, our skies would go dark, and you and I would cease to exist. So let us appreciate the diversity of reactions that exist in our universe and make life as we know it possible.
Pizza